When preparing for ACI certification, candidates immediately encounter a specific limitation built into the reference package. The job task analysis strictly requires you to know two specific ASTM standards, ASTM C1140 and ASTM C1604. But the full text of those documents is intentionally left out of your study materials. You are expected to understand how these standards govern the inspection process. However, for exact dimensional tolerances, correction equations, and specific reporting language, you must consult the actual ASTM documents themselves as the ultimate controlling source. To understand the job task analysis, we have to look at this primary standard dichotomy. Shotcrete quality control is divided into two distinct pathways. On the left, ASTM C1140 governs the panel. Its precise role is preparing and testing specimens derived from shotcrete test panels. On the right, ASTM C1604 governs the core. Its focus is obtaining and testing drilled cores of shotcrete. The numerical output generated by a compression machine is entirely useless if the initial specimen preparation is compromised. Testing quality begins long before the concrete reaches the laboratory. Memorizing this specific division is critical for the exam. Applying a core extraction tolerance to a panel preparation question, or vice versa, shows a lack of procedural understanding and will result in a failure on those specific questions. We begin with ASTM C1140. The job task analysis expects you to master the requirements for test panel form geometry, appropriate materials, and the strict procedures for curing and conditioning the concrete. The standard dictates a precise chronological pathway. You shoot the panel, cure the panel, extract the specimen, condition it, test it, and finally report the data. ACI 506.2 relies heavily on this standard, specifically referencing C1140 for the proper conditioning of test panels up until they are transported, and for the exact method of obtaining specimens. Within that extraction phase lies one of the most critical physical limitations of the standard. You cannot drill a core from just anywhere on the panel. Extraction locations are strictly controlled. This diagram illustrates the mechanics of the edge effect. As shotcrete is applied, high-velocity air and materials strike the formed edge. This interrupts standard airflow, creating turbulence and trapping defects, specifically sand lenses and voids, near the panel's sides. Because of this aerodynamic reality, ASTM C1140 strictly limits how close to a panel edge a compression core may be extracted. Cores pulled from this outer boundary zone contain trapped rebound and voids that do not represent the normal internal placement of the structural concrete. Violating these spatial limits generates false data. You might extract a physical cylinder that perfectly fits into a compression machine, but the test is procedurally invalid because the specimen no longer reflects the strength of the overall structure. Once the specimen is extracted, the governing rules shift to ASTM C1604. Here, the job task analysis tests your knowledge of proper core sampling, moisture conditioning, and specific core geometry. This initiates a new procedural sequence. Select the location, drill the core, identify it, handle it carefully, condition it, prepare the ends, measure, test, apply corrections if required, and report. A common error in the field is assuming that once a concrete cylinder is out of the panel, all cores are mathematically equal. Drilling is inherently destructive. The force of the diamond bit grinding through aggregate can induce microcracks or chip edges, invalidating a subsequent strength test. Core geometry requires equal attention. The length to diameter relationship of the extracted cylinder dictates how the material will behave under immense pressure. Moisture conditioning is also strictly controlled. Compressing a dry core yields entirely different load data than crushing the exact same material after it has undergone a required soaking period. Before testing, the bearing surfaces must be addressed. Sawing or capping the ends of the core is a structural necessity, never a cosmetic preference. If you place a poorly prepared, jagged core into the machine, the hydraulic plates apply pressure at irregular contact points. This creates non-uniform loading, forcing the core to break prematurely and yielding an artificially low strength result. When a core's dimensions fall outside the standard reference geometry, such as an unusual length-to-diameter ratio, the standard requires the application of specific mathematical correction factors to make the result valid. The drilled core ultimately serves a dual purpose. Generating a numerical load value in the compression machine is only half the equation. The machine evaluates strength, but visually inspecting the exposed surface of the core evaluates workmanship, revealing critical details about internal consolidation, reinforcement embedment, and substrate contact. Finally, all of this physical precision is wasted without proper administration. A specimen arriving at a lab labeled simply Core 1 provides zero value for quality control. Valid traceability relies on strict parameters. The inspector must document the structure, the exact location on the panel, the date of placement, and the required test. C1604 exists entirely to protect the integrity of the specimen post-extraction. Without these strict physical and administrative controls, the laboratory test is compromised before the machine is ever turned on. To apply these rules as the certification exam expects, let's evaluate 3 practical field scenarios. Scenario 1. A test panel is shot correctly, with quality material, but the inspector drills the cores directly beside the formed edge. The issue here is not the volume of concrete obtained. The issue is the representativeness of the sample itself. Drilling here explicitly violates ASTM C1140. Due to the edge effect and airflow interruption, the sample is likely full of sand lenses and voids, which makes it completely useless for any structural validation. Scenario 2. 3 structurally perfect cores arrive at the testing laboratory without clear location labels or placement dates. The testing machine does not care about paperwork. It will still crush the cores and generate accurate load numbers. However, a lack of traceability breaks all QA/QC protocols. The project engineers cannot confidently establish what batch or location those numbers represent, rendering the test invalid. Scenario 3. A core is extracted, but it features an unusually short length to diameter ratio. If you simply test the core and report the raw mathematical strength displayed by the machine, you have provided inaccurate data. ASTM C1604 mandates the application of specific correction factors. These calculations adjust the raw data to ensure the non-standard geometry produces a result comparable to the standard reference cylinders. Keep the exact boundaries clear for the exam. C1140 governs the rules of the panel. C1604 governs the rules of the core. A final reported test result is only as reliable as the raw specimen and the exact process that produced it.